Surat. I welcome each of you to the second session of 7th day of International Virtual Workshop on Global Seismology and Tectonics. Today we have with us Professor J.R. Kyle as a session chairperson and Professor Sebastiano D'Amico, University of Malta, as a chief guest. Today, the speaker is Dr. Saurabh Baruah from CSIR-NEIST. He is going to speak on the complex Seismo-Tectonics of northeastern region of India. But before he delivers his talk, may I request our session chairperson, Professor J.R. Kyle, for his initial remarks. Over to Professor J.R. Kyle.
Oh, thank you, Shantanu. Thank you so much. It's my great privilege and great pleasure to be chairing this session. And today's speaker is Dr. Saurabh Baruah, Chief Scientist of NEIST Jorhat. He is sitting with gray hairs and white beard and looking, a towering personality. Saurabh Baruah is always a very kind, warm, loving young brother to me. I know him for last 30 years, some three decades. He first discovered me. Possibly he came to know about me from publications, and sometime in 1994 or so, he visited Calcutta and visited GSI to meet me. That was first time I met Dr. Saurabh, a young man with enthusiasm of doing seismology, and he gave his introduction to me. So since then I know him. Then eventually we became very brotherly, and he also became a very key scientist in then RL Jorhat. And since early 2000, we are on Indo-Russian collaborative projects, international project, since early 2000 to 2013 or so. So we had long association in international projects. He was the co-PI, then he was also PI for some projects. So like that, we were working for last 30 years together. And he is a man who is very good in computational seismology. Any new work, any new program, if it is available through person or through internet, he will download and he will try to do the analysis with the new program. So I think on any subject, right from waveform inversion to stress tensor inversion, to anything and everything, Dr. Baruah was very active, very dynamic seismologist of NEIST, and my very loving brother, my very loving colleague at the same time. At one time, there are some half a dozen PhD students under him when we were in Indo-Russian project, and we all used to work together. So that was the golden time when I used to come almost 3 times a year to NEIST and work together. So I have a very long memory, very fond memory with NEIST and with Dr. Baruah and his whole team in that laboratory. So actually I love that laboratory, I love that place, and more so for Saurabh's very warm heart and warm hospitality. So anyway, I can go on talking about him, but I think I must stop here. So today, I think he is one of the most veteran seismologists, man of the soil in Northeast India, who records earthquakes, who analyze earthquakes, who interpret earthquakes. So today evening, we have a great speaker from NEIST Jorhat, who will speak on Northeast India earthquakes, Northeast India tectonics. So over to Shantanu, please.
Thank you very much, sir. Now, may I request our chief guest, Professor Sebastiano D'Amico, for his remarks. Over to Professor D'Amico. Professor D'Amico.
Thank you, Santana. Good afternoon, everyone, and good evening to everyone. Thanks for the invite, and very well done for this very organized. I'm pleased and very honored to be part of this team, and I'm sure that the lecture of today will be an excellent one and very informative about the complex seismotectonic setting of North and East India. I have shorter memories than Prof. Kayal. My interaction with the NEIST is quite recent, and I'm pleased that I start collaborating with the NEIST, and I had the great pleasure to be in Jorat last February before the whole pandemic took over. But I really hope to come back again and to start profitably to work and to study that part of the world much more, and to have a profuse and a very fruitful collaboration with this excellent team of scientists. I shall stop here and leave the floor to Dr. Baruah for the next steps. Thank you.
For your let me read out a short bite of Dr. Saurabh. Dr. Saurabh is working as the chief scientist at CSIR-NEIST Jorhat, Assam. He is a prominent research scientist in the year 1996 University of Assam. Decades in the field of seismology. Dozens of PhD theses have published of the research papers in different national and international journals of repute. Journals too. He was one of the network of network around northeast region of India. Of the Brahmaputra River at Tensor, Assam, for northeast region of India. He was one of the winter members of 18th Indian Scientific. We indeed glad to have access this international virtual. So may I request Dr. Baruah to deliver it. Over Dr. Baruah.
Thank you, Dr. Shantanu. Thank you so much, Professor Kayal, sir, and Sebastiano. Good evening, everyone.
Sir, excuse me, sir. Professor Ramesh Singh also online. You can greet him also, sir.
Yes, Professor Ramesh Singh as well. Nice that you all are on this lecture. Indeed, it's a really great pleasure and privilege that we are attending this international virtual workshop on global seismology and tectonics, and it has been today maybe the 5th day of this virtual workshop, and very important topic that has been covered through this lecture, that is complex seismotectonics of northeastern region of India. Why it is complex, what is the complexity parameters that will be discussed here, and these complexity parameters are not only seismological parameters, very vivid geology is involved, geomorphology is involved, and above all, the present day geophysical investigations that are really an important aspect that I will try to cover through these particular deliberations. If we happen to see 160 million years ago, Jurassic earlier Cretaceous time, that the movement of Indian plate towards the north, and this is as a whole we say as a greater India, and there is a Tethys Sea surrounding, and it is included with Antarctica and Australia. And gradually, by 59 million year late Paleocene area, what we have seen that there is a northward movement which has really developed a significant entity that is Proto-Himalaya, and subsequently there is a delta accretion zone and delta progression along with the subduction which has been observed in this progression. And gradually, when we see in 44 million year late Eocene, the entire scenario is almost clear to us. Himalayan collision boundary has formed, and it has reached maximum to the east, and its syntaxial band serpents, and it wide ocean basin. It's a wide ocean basin still, and we'll see that ocean basin where it was just at this juncture, and gradually the delta progression stops, and that way the present day scenario that we find that total Himalayan four-deep zone is very much unstable. There is a subduction zone to the east. There is a delta basin in the, what we call Surma basin at the at this part of this northeastern region of India, and this particularly gives a really varying tectonics types, tectogenes. So these varying tectogenes is the source of attraction for many of us, and if we really see this particular map, present day map from Creamer et al. 2003, then we find that the progression is the directivity, GPS directivity map indicates that it is moving towards northeast, and there is a Himalayan boundary, and entire, if you see, there is a rotational movement at this region, these regions. This is a rotational movement, and if we happen to see, this is a 40 millimeter in the Arabian Sea, and this is 55 millimeter per year along Bay of Bengal. So there is a relative velocity. Sometimes it is observed that it is pushing straight way with a higher rate here and with a relatively lower rate here in the Arabian Sea. But the most interestingly, there is a rotational point. That means when there is a rotational point where we get Java, Indo-Myanmar subduction zone, and it is connected to Java, Sumatra as well. But why there is a rotational point? What is the reason? Because there is a movement from southward direction and there is a movement northward directions, and as a result there is a contraction between this Shillong Plateau and the Himalaya, and this being the cornermost part of, rather extensional part of Indian plate, what we see exactly, I mean, this is really a complex reason. And when we look at the rotational point, which has been said in 90s, the rotational point is somewhere in this part. And when we look at the rotational point, this point is nothing but the Wenchuan province of China, which is hardly 300 and less than 300 kilometers away from India-China border. And in Wenchuan, we know what happened in Wenchuan provinces. And that provinces say that on May 12th, 2008 at 2:28 p.m. an earthquake measuring magnitude 7.9 on the Richter scale happened in Sichuan. 391 dams were damaged by the earthquake. 69,000 people were killed. 3.7 million injured. Almost 18,000 people listed missing and 4.8 million people homeless, which has just happened 300 kilometers away from Indo-China border of northeastern region of India. And exactly at Sichuan province, the city has been built on the fault line, and this is the status of that particular city. And in that city, we never had mapped the fault through active fault mapping. We never had the seismic hazard map. We have built houses on the highly elevated zone where topographical amplification occurred. And what we see here, maximum of the houses are totally damaged, you can understand. And exactly that Indo-Tibetan or Indo-Eurasia, that rotating point, at the point of rotation, all these happened. And we are not knowing that we have built a beautiful city just on top of a fault line. This city is now totally abandoned. Had we made the proper seismic hazard assessment, this scenario wouldn't have happened. So what we saw from this earthquake, this is 1950 earthquake, and the Wenchuan 2008 earthquake is somewhat near here. Professor Kayal has described the stable continent SCR earthquake, all the earthquakes of other parts of India, in Gujarat, Jabalpur earthquake, Killari earthquake. I would like to stress upon two great earthquakes that has occurred in northeastern region of India, that is 1897 and 1950. And in a process, what is the lessons we have learned from this particular area? The rupture is unknown till date. What is the extent of the fault? That is also unknown. So these are some of the questions that is very much prominent towards development of a proper seismic hazard map of northeastern region of India. So when we see complex tectonics, seismotectonics of northeastern region of India, we must have to see the northeast in a very holistic way. This is Arunachal Himalaya, which is part of Tibetan Plateau, we can say. This is a collision boundary. And this is the syntaxial band. Sichuan province is, Wenchuan province is somewhere here at this point. There is a Rima Valley, 1950 earthquake occurred. From China, we see, or Tibet Plateau, we see three big rivers. that is coming down. This is Siang River, and this is Lohit River. This is Dibang River, and this is Lohit River. And if you happen to see, this is the Himalayan front thrust zone, which we call sometimes HFT, and just little beyond there is a MBT. This is beyond, this is full of shivalics, and beyond MBT there is a, it has started main crystalline thrust, what is prominent here, which is nothing but an Himalayan orogenic belt, as we understand, as we know. And if you happen to see to the east, it's the most interesting zone. And why it is interesting? Active subduction is going on here. And today, this morning at 7:30 IST, 4.6 magnitude occurred in this Indo-Myanmar subduction zone. And if you happen to see, this is the alluvium plain of, that is we call Brahmaputra Valley. This is the Brahmaputra River. And these Brahmaputra rivers, its the length is almost 700 kilometers, and it passes through Brahmaputra Valley, and right now it is devastating with its floods fury. And while crossing the Brahmaputra, there is a place called Kaziranga Sanctuary in this basin, where only one horned rhino is available. And beside that, there is an extension of Shillong Plateau. This is called Mikir Hills. And this is entirely Shillong Plateau. If we happen to see Shillong Plateau, this is the Dauki Fault, and this is also extended almost more than 500 kilometers. And as you see, there is some fault existed here, and which I'll come later. And gradually, this Brahmaputra crossing the Surma Basin goes to the Bay of Bengal. And if we see this subduction zone, this is the accretionary zone, what we see totally compressed zone. And here I'd like to mention, today morning while Professor Kayal was delivering one question, answering one question, that is Bagjan blowout site. This is the area where that Bagjan blowout site occurred, and it is full of oil deposition here at this point. So we remember Siang River, Lohit River, Dauki Fault, and all these places will roam around in a few minutes of now. As I just explained, this is the 1897 earthquake. The rupture is still unknown. This is 1950 earthquake. This is tentatively placed here. This is in Rima Valley, where there is two large thrusts, that is lowest thrust and Misumi thrust, it existed. And here exactly which is the particularly rupture area or which is the epicenter, that is still unknown. And apart from these two large earthquakes, there is 7 large earthquakes also occurred, which is greater than 7 here. And as we see, as I mentioned, this is the MFT, and this is MBT, these big lines, red lines, and this is the MCT, and where you see the Indo-Myanmar subduction zone, and this is the San Sagaing fault here. And this is in accretionary zone. This is a beautiful city, Aizawl is situated, and right now Jorhat is somewhere here. Jorhat is somewhere here. We are calling from Jorhat. And as mentioned during Professor Singh's lecture, that we have a multi-parametric geophysical laboratory, and that is situated in this particular region, that is Tezpur. And beside Tezpur, there is a mega fault, that is, which is produced again 1943 7.3 magnitude earthquake, and this is called Kobali fault. And again there is another fault which is not available here, shown here, that is Bomdela fault, flanking that Tezpur region. Why it is flanked? And that we understand from this GPS directivity map along with the strain map from Unavaco. This is the highly stressed zone where MPGO is situated. And as I said, if we happen to include the GPS directivity map, then we see this is there is a complete rotational view as we understand. And this is the highly strained region, and this has been taken from Unavaco website and superimposed with the faults and lineaments and the mega thrust on this particular map. And when we look forward, the 15th August 1950 great earthquake of magnitude 8.5 and above, then here we'll try to see there are a lot of studies has been made, but still rupture area is unknown. So we'll look for the rupture area. There are some of the, I being a seismologist, sometimes worried about that seismology, just recording earthquakes and go for, analyzing and interpret and through the focal mechanism solutions and stress tensor inversion and subsequent tomography and all. But that is part of seismologist. But there is a big role to play as a part of structural geologist, geomorphologist, and as a geologist. So being a part, I always wanted to roam around with the seismology, geologist and geomorphologist. And as a result, we saw some of the unique features. Of course, it is from Kingdom and Ward paper on 1950. What we see here in this figure that has been taken from King and Ward on 1950, that a lot of stones, rocks, and that is embedded inside the tree trunk. And why it has been embedded? What was the furious nature of 1950 earthquake? What was it? Totally turmoil, the reason? So that the stone rock mass was lifted up and embedded inside the tree trunk, and that was a big question here. That means a rock mass may be segregated from a bigger rock mass and lifted up and went inside, hit the tree trunk and got embedded inside this tree trunk. So it gives us a very big information. So for seismic hazard is consistent. That means this has particular earthquake of 1950 has produced more than an acceleration greater than 1G. And as a result, that stone mass was broken up, or stone mass was uplifted from the base and entered hit the tree trunk and entered inside the inside this particular tree. So this is also from Kingdom and Ward, and this is the landslide, and where he mentioned that hills split in half by the earthquake. And this was the picture taken just after 1950 earthquake by King and Ward. And when we see there is a splitting, the splitting he tried to mention somewhere here, I think. But very recently, when we move, very recently when we move to the area, this is just at the bank of River Lohit, we see there is a huge landslide. And it has been established that the earlier, this entire landslide was due to 1950 earthquake. And as I mentioned, that this particular figure and the last figure, what I showed, this is the same figure. This was taken, just after the 1950 earthquake, and that particular figure was taken just recently. And when we see a place called Demui in the Lohit River, that there is a bridge, and that's from that particular bridge, this particular figure, photograph was taken. And when you see the photograph, then here we see some kind of abrasion That means what has been established that there is a huge fault dominant abrasion is here, and that fault is passing along this particular region. And when there is a huge amount of water flows during monsoon, and as a result there is a cause of this abrasion, during that particular, maybe during that particular earthquake. So this is some of the features that we wanted to see. And when we moved to the syntaxial region, there we saw another typical geomorphological features. And if you see, this is the inaccessible terrain in the river side. During winter season, these are very, very much visible. If you see the 4-layer grass layer, tree layers, 4 layers of tree, and these are nothing. This is the oldest scarp, and this is the recent scarp. And from vegetation itself, we could demarcate what are the fault scarp, and what could be the probable rate of upliftment. And that way, when we visited all those places, searching the fault scarp, then it has been another river sections we have found that this is the scarp, and the fault line is maybe passing through this particular region. So that way it has been established as well in Siang River to see the remnants of 1950 earthquakes, or what is the exact geodynamic figures and the tectonic figures. As I mentioned, that Siang River, this is flowing through Arunachal Himalaya from China, and it is just at the foothills of Arunachal Himalaya. This photography was taken, and if you see the stratigraphy of the bed of Siang River, it indicates that it is oriented towards south. The dip is oriented towards south, and many more interesting features we observed near the banks of Siang River. Uplifted quaternary sediments, and this is the quaternary sediments in the river banks, and of course due to active tectonics, soft sediments intrusion in clay. All these were visible along the bank side, and this is the exactly taken, this figure was taken from the roadside. Just it is the roadside between the river Siang and this particular bank. And now what we conclude from here, either this is the particular bed, river bed uplifted, or maybe the present Siang River has eroded down to the present strength, present condition right at this moment. But as we understand, there is a lot of pure sand observed here, and this sand obviously the remnant of Siang River only, which we call as a quaternary deposit. So these are the features that has exclusively indicated that how active the region was when these all happened. And we visited this particular place, and this is it's a very interesting region to survey around. And this is Rowing Fault Scarp here in a place called Rowing, and we have identified 14 feet fault scarp, and we have also tried to understand what is the fault rupture here at this point. And there is a prominent river, that is Kamlang River section, and this Kamlang River section, as we understand, this is the fault scarp. Is the fault scarp, and the fault is moving along this direction, it's dipping along this direction. So this could be, this is the fault is crossing the river at this point. And as we understand, when we go to the near Teju in a called Wakro fault scarp, and this is a place called Wakro, where there is a big sanctuary available there. Also we could find what is the uplift of the fault scarp, that is something around 8 feet. So all these conclusion, all this information helped us to understand what is the rupture extent of the rupture area due to 1950 earthquakes. And a lot of studies has been done on this particular thing to understand the complexity and to understand the contribution of 1950 earthquake through active fault mapping, which has been published recently in EPSL 2019. So as we understand 1950 earthquake, we go to the 1897 earthquake, Great Shillong Plateau earthquake. And again, I have explained this particular figure already, but this particular figure, this is the extent of this hat type figure you see here as well somewhere here. This hat type was the rupture area as estimated by Oldham, R.D. Oldham. But equally, this isoseismal map, apart from this isoseismal map, another interesting map sketch Oldham in 1899 published, he has drawn. This sketch is like this. There are two, this is a beautiful sketch. There are two pebbles again here, which was somewhere here. This is the original place of these two pebbles. This is the original place of these two pebbles. And these two pebbles were lifted up and it has come up to this level. So what it indicates? It indicates the same conclusion. That means that 1897 earthquake has also produced an peak ground acceleration, which Professor Susan Ha yesterday mentioned, that it has exceeded the peak ground acceleration of more than 1g and nullified the Earth's gravitational pull and uplifted and tossed up and almost thrown almost 5 meters away. This particular figure is a very good indication for seismic hazard assessment right at this moment. So as we understand, the Shillong Plateau we have talked upon, and this is the isoseismal map of 12 June 1897. It has devastated almost up to Jabalpur, up to mid-India region, Tibet, Himalaya. And also here there is a very good monastery in Tawang, Arunachal, Himalaya, that was totally devastated, I mean destroyed during this particular earthquake. And of course in Koch Bihar, there was a 3-storied palace, and that 3-storied palace, the ground floor was totally subsided inside the earth. So those are the I mean isoseismal map that has produced. And the most severe part were the western part of Shillong Plateau, and of course some parts of Assam Valley. As we understand, to understand the remnants of 1897 earthquakes, again there is a beautiful flexure of rocks observed deeping south in near Dauki Fault, Meghalaya, and this beautiful flexure is just throughout near Balpakram Fault and Balpakram sanctuary, which is in the just receded in the Indo-Bangladesh border. As we go, as I said, there is a lot of limestone quarries, and this is in Balpakram National Park, Meghalaya. It is near Indo-Bangladesh border as well. And as I said, it was totally in ocean. The entire Himalayan frontal thrust up to Himalayan frontal thrust, Bay of Bengal, oceanic water, oceanic involvement were there. And when it has receded, it has eroded the entire limestone rock mass throughout. And why it is a oceanic? Because there is an existence of a lot of nummulitic embossed limestone in that particular area region. And all these features has evolved the complexity of geotectonic behavior of northeastern region of India. As we understand the Bangladesh, this particular region will see what is the remnants, and this is the Bangladesh border, and there is a beautiful roadable road, almost 400-kilometer approachable road is there, and there is a flat quaternary. This is a totally a basin, and here is a sandstone, and this is always south dipping bed, and which is pushed towards north, and this is the Dauki Fault, remnants of Dauki Faults of what we are observing, we have seen there itself. And more interestingly, We have also seen nearby, just it was a photo was taken from the footwall, and inversion of riverbed we have seen, and this is a textbook kind of shear zone what we have seen alongside the river. This is near Kachipara and Indo-Bangladesh border. That means this particular thing exactly indicate that how much tectonically active the entire region is presently. And as we understand, it's a STAR-DEM map, and when we see the observe the STAR-DEM map, then you see here this is the Dapsy thrust, and this is a dormant trough, so no much activity we observe here. And this Dapsy trough, if you happen to see the elevation map somewhere here, and this is the topmost region somewhere existed here at this place. This is, and beyond these, very interestingly, there is a faulted zone. There is a folding. This is between Bangladesh plain and Chakpur thrust. There is a folding going on somewhere here, and this folding is maybe due to the huge convergence of extension of Himalaya, Indian Himalaya or Indian plateau, or maybe the Meghalaya plateau towards Bangladesh plain could be the probable information that why this folding is occurred. So this folding is very much prominent for us right at this moment for seismic hazard assessment. So with all this information, we have tried to we have rigorously visited all these places in 1950 and 1897. And in 1950, entire fault scarp could be evaluated, and which has been published in EPSL 2019. And entire rupture area could be extended from seismicity point of view, and also from these geomorphological features. And that was, but we are yet to resolve the issues somewhere here in this part of the 1897 rupture area. As I understand, the complexity is very much reflected in elevation map. In Assam plain, if you happen to see this CC' profile, and this is the Assam plain, and this is Assam plain, and this is the Indo-Myanmar subductions ranges, which we call also belt top Shupen, and somewhere in volcanic line, then Sansagang fault. This is very much prominent here in this elevation map. But to our surprise, when we see the gravity map, when you see the broad gravity map, there is really a variation in gravity throughout the terrain, throughout this section, and it is visible. We have taken so many sections, and in all sections it is prominent. When we try to see again the magnetic anomaly map, here also we see the variation of magnetic anomaly, and this itself indicates that the vivid nature of geological condition underneath this particular region. And so far the seismicity and depth section is concerned, because as I said, it has produced 2 great earthquakes, and it has produced 7 large 27-point magnitude earthquakes. So daily lot of earthquake comes. Today morning also 4.6 magnitude came in this particular region, in the Indo-Myanmar region. And if you happen to see, if you close your eye, if you happen to see, this is the seismicity map. This is the seismicity map from ISC database from 1897 to 2017 plotted. And here it is the regional network. We have a network, and this regional network was established in 1984, and up to 2017 it is mapping the entire seismicity scenario in northeastern region of India, and that's why you see the cluster of events is much more higher here, and that way if we see the depth sections and these depth sections, east-west depth sections, then we see the Indo-Myanmar subduction zone. The earthquake is sometimes around 120 kilometer. And if we happen to see the depth section plot of this, it's a very interestingly in Indo-Myanmar region it is up to 120 kilometer, but throughout the northeastern region of average seismogenic zone is 45 kilometer. So it's really a highly seismically active zone. And if you happen to see, if you close your eyes and put your finger on this map, you find an earthquake epicenter here. But what is the happening at depth? That when we try to see at 0 to 45 kilometer depth, we see that there is a lot of earthquakes in 0 to 45 kilometer. I mean, a little bit devoid of in Assam Valley. In the Myanmar, we see a lot of earthquakes. But when we go to 45 to 90 kilometer, then yes, Indo-Myanmar subduction is very much active, but rest is decreasing, except somewhere in Tezpur region. And when we go above 90, then we see the seismicity pattern still exists beyond 90. I mean, so as we understand, this particular region subduction zone is very much active, but where we don't see much earthquake, we don't see at all earthquakes. And this may be the, I mean, some of the earthquakes which is not overestimated. But the thing is that this particular area, northeastern region, is almost seismogenic zone we consider for seismic hazard assessment, something like 45 kilometer depth. So that was the scenario as we understand. As this is a and workshop we are organizing, so little bit of theory I would just like to indicate that what is exactly dynamic elasticity, and which is nothing but a theory of elasticity. Here for these earthquake occurrence we record the earthquakes, and what is these earthquake? We call this earthquake record as seismogram. That is nothing but UT, and this seismogram is the combination of three important parameters, that is source parameter, medium means the path from the source to the recording station, and the instrument response. That means the whether your instrument is totally calibrated one, you know the digital instruments I mean counts per se versus ground velocity. So when we multiply all these source effect, medium effect, and the instrument effect, then entirely we get seismogram. And here theory of elasticity follows Hooke's law, theorem of uniqueness, and reciprocity theorem, and of course this medium we call as the Green's function. What is Green's function? That Green's function is nothing but the seismic impulse response of the earthquake of the medium, seismic impulse response of the medium. Now we actually infer this seismogram as a time domain as well as a frequency domain. It is our choice how we move forward, either time domain or frequency domain. But we have to know very important point that our seismogram is nothing but it's a combination of source effect, medium effect, Green's functions, and the instrument effect. Now a simple equation allows you to understand about the source effect. This is the simple equation. This is the seismogram divided by the Green's functions divided by the instrument response. So when you divide this particular seismogram with the Green's function and the instrument's response, the amplitude division, maybe the frequency division, so there you understand exactly the source characteristics. So I'll just touch upon a little bit on the very important aspect, what we can do of seismogram after digital invent of digital seismograms, and we can determine focal mechanism solutions. This is the best predicted model right at this moment, and this best predicted model is a kind of model which is I mean worldwide it is used, and as it is a workshop, I'll just to say that means there is a in amplitude spectra inversion and whole waveform modeling we call, and the first step we use for this whole waveform modeling, that is nothing but we consider time, latitude, longitude, depth, and moment magnitude, seismic moment, not moment magnitude, but the seismic moment. And after knowing the whole waveform, and we try to infer the centroid location where it is time domain inversion. This is the steps which is very much available in literatures, but again I just want to touch upon these particular things. And when we see the time, latitude, longitude, and depth, and seismic moment, therein we incorporate one more point, probable one more point, that is strike, deep, and rake. And this strike, deep, and rake, when we infer, we probably we infer, we try to do incorporate one kinematic model. These are the three steps we have to understand. And there in kinematic model, what we do actually amplitude spectral inversion, and it can be through P wave inversion, it can be through S wave inversion, it can be through total waveform inversion. And here we try to see the strike, deep, and rake of the earthquake, and rake of the earthquake. And what you may ask, what we try to understand? We try to understand the focal mechanism solution. As Professor Kayal has already mentioned, what is focal mechanism solution? That it infers that strike, deep, and rake. And there is two planes. What is the exact focal plane that we can infer out of this particular method? And the strategy shows that this is the source characterization, and you have raw earthquake. This is the raw seismogram, and this raw seismogram you just invert and try to create the synthetic seismogram. And when you try to create the synthetic seismogram, you try to combine the raw seismogram with the synthetic seismogram, try to match rather. And when you try to match the amplitude during that process, when the amplitude is totally matching, both for raw seismogram and synthetic seismogram, in that case, what you establish, there is a barest minimum error, what we call RMS value. When there is a barest minimum RMS value, we can infer exactly what is the strike, deep, sleep of that particular waveform inversion. And here, very importantly, we have to have a very good crustal model, and that way you find the through waveform inversion the focal mechanism solutions, which gives you the idea of focal mechanism solution, and that way you can characterize the source. So we have seen what is the source characteristics of Dauki fault, and this is the strike slip in Dauki fault what you observe, and this is sometimes we also get normal faulting in Dauki fault. So this is somewhere we have some scientific questions still, whether it is a normal fault, whether it is a strike slip fault. This Dauki fault based characterization yet to be made, but it is true that it is always north dipping, and the trend of the strike is east-west. So that way we characterize the Dauki fault. Same way, the Tista fault also we have characterized, which is absolutely strike slip fault. And if you happen to see the Dhubri fault, which is also, which has all these fault has gigantic fault has produced,
more than 7 magnitude earthquake, and this is the trend is north south, and this is the trend is north south. So that way you can characterize the fault, and this is the normal course of action for a seismologist to understand the focal mechanism and characterize the fault, because ultimately it will be the input to the seismic hazard assessment map. That way also we have assessed the syntaxial zone, as I said, the near 1950 earthquake. So when we characterize the sources, then we are able to understand the fault behavior, fault nature, and above all, we can infer a very important parameter that is known as seismic moment. And that seismic moment is nothing but seismic, it's energy out of that particular earthquake. So that is a very important information that we get from source characterization. So this is the beautiful tool which is now very much available worldwide usage, and we must avail these particular tools to characterize a fault. And here if you see, this is the particularly Indo-Myanmar region, and this Indo-Myanmar region in overriding plate, in plate boundary, in Benioff zone, this particular earthquakes, whatever occurred, and this region wise we have characterized the entire source domain, and this gives us an understanding about the behavior, seismic behavior of that particular seismogenic zone in Indo-Myanmar region. That way, see a vivid representation of focal mechanism solution throughout northeastern region of India. And throughout northeastern region of India, when we see, we based on the earthquake, seismicity, focal mechanism solutions, what we did, for hazard mapping, we have devised the entire region into 10 seismogenic zones and 10 different seismic identity. And these 10 different seismogenic zones, one thing we have followed, it is a mixed kind of focal mechanisms available, and this mixed kind of focal mechanism, what is available, that is exactly not very much clear to us. That means which is prominent mechanism existed in northeastern region of India. So this is also another questions that we should try to resolve, that which kind of focal mechanism solutions is pertinent to a particular region that is yet to be resolved. So now this particular output or the focal mechanism solutions, where we get information about the strike, deep, and ray, and this strike, deep, and ray can be the input for another estimation which is called stress tensor inversion. And if you see the world stress map, this world stress map is a replica, it has been estimated from in situ measurements, fault fractures or fractures, but not exactly from focal mechanism solutions. So as a seismologist, we can also make an input to this particular earthquake, stress map. And as we understand, this is called stress tensor inversion. And here we have to know this, where is the stress condition. This is well known to all of you, the students, particularly the new students who are budding seismologists. They must know that this particular feature zone, in the form of a cube, are replicated with the 3x3 matrix and having 9 components. And if you happen to have a tensor stress, you cannot define the because it is scalar quantity, so you have to transform and incorporate the tensor. And when there is a stress tensor, exactly you can invert to a domain where we really try to resolve the shear stress, and which is just like this. It is S11, S22, S33, which is sometimes we called as sigma 1, sigma 2, and sigma 3. And in this case, one thing is prominent, that sigma 1 is the highest one, sigma 2 is the intermediate one, and the sigma 3 is the the least one. So when we can infer the sigma 1, that sigma 1 itself gives us a peculiar establishment. And how we do, just I'm touching upon for the budding seismologist. If you happen to have focal mechanism solutions for your reason, please do send us the input file. Please prepare an input file with dip direction, dip angle, and slip. Utilizing strike angle, dip angle, and the slip angle. So what is dip direction? This is dip direction has to be, this is strike plus 90 degree. That is the dip direction. You have to have some degrees of strikes, and plus 90 degree, it gives you the measurement of dip direction. And then again, one condition is there: if dip direction is greater than 360, then dip direction you have to do like this, dd minus 360. And as a whole, this dip direction is very much important, which is a dip direction on this input file. And this is less than the dip direction you keep as it is. So this is the format how you have to prepare the input for stress tensor inversion. Now, after this, there is a good point, that means best resolution. There is a point what I prefer to you all, that means you just prepare for your reason the strike, dip, and rake, and the dip direction, dip and rake, and send the file. I will try to do some kind of work for you for your reason along with your Seismo-Tectonic map. And that way, what we have done, we have employed that output of focal mechanism solutions, and you see here, and this has been published in BSSA by Dr. Shantanu Baruah et al. And you can go here where Professor Kayal and myself is also co-authors. And here we have just seen the earthquakes epicenters, and these are the crusts, some of the what we call cluster of earthquakes. So cluster wise, when we have inverted, try to understand the sigma 1, how it is behaving, and this is the status of sigma 1, as you understand. And mostly we have inferred for these two reasons, for cluster wise, depth wise, and of course reason wise. And that way we get a lot of information from focal mechanism solutions through in stress tensor inversion. Now you see here a very important information what we observe. What we see, this is the depth range 0 to 45 kilometer. This is the depth range 45 to 90 kilometer, and this is the depth range 90 to 160 kilometer. Now, as we understand, if we see the stress tensor inversion, that means the orientation of principal axis sigma 1 at deeper depth, at lower depth, it is almost northeast directed. It is almost northeast directed. If you go little deeper, that is for 45 to 90 kilometer depth, and it has come closer to north, the sigma 1 has oriented towards north. Earlier it was northeast, but it has come towards north. But when it has gone down 90 to 160, it has almost oriented towards north-south directed, which is the trend of Indian plate margin, which is the trend of Indian collision convergence zones. So these are the some of the features that we could infer from this particular stress tensor inversion. And as I understand, this was published in Geophysical Journal International in 2009 by Professor Late Angelier and myself to this work. And likewise, we have also done depth-wise what is the synthetic stress map, and this is the entire domain characteristics what we see right at this moment in that particular publications we have published. And this is peculiarity is that in Shillong Plateau, if you happen to see the Shillong Plateau, rest of the plateaus is almost rest of the places are almost oriented according to the geodynamics, but Shillong Plateau is something unique. Why it is unique? It is western part of Shillong Plateau is sigma 1 is acting along this direction, not northwest directed, but in eastern part of Shillong Plateau it is northeast directed. So this is the peculiar findings that has been carried out here, and a lot of receiver function analysis, a lot of anisotropic analysis has also been carried out, which is not being discussed right at this moment. So that way, depth sections also we have inferred, because these all information is the prime input to the seismic hazard assessment of this. And this is a very well-known figure. That means with different GPS studies, we have tried to see how the velocity vector is varying and moving. As we understand, this is the GPS velocity vector with 14 to 15 millimeter per year in Shillong Plateau, and this is directed, and this is also directed towards this direction. This is with RTR reference frame. This is with Lhasa, and interestingly, what we observe from here that what is inferred from stress tensor inversion, that is on synchronization with these two different reference frame. And this is a point of question. We have to why this from two different reference frame this is being resolved along these two stress axis, principal stress axis. So this is a very important question that we are yet to answer why it is so. We have also done seismic tomography. As I understand, this tomography with 54 seismic station data through LET, local earthquake tomography, and very interestingly, at 20 kilometer depth, we have inferred some of the very highly low velocity zone, and this low velocity zone persisted in near Kopili fault region, and when there is a low velocity zone along a fault region, fault structure, and that is that means act as a stress accumulator, and probability could be there. There is a probability of occurrence of an earthquake in that has been inferred through these particular tomograms, and which is yet to be published. It is not published as of now. As I said, had Sichuan province known about the probabilistic seismic hazard assessment, the devastation wouldn't have been so much. So whatever I showed in this map, and ultimately this is where we have to end up for the earthquake resilient society, and this is a very known map. And following this map, we have devised the seismic hazard map of northeastern region of India. As I said, complexity, it is totally complex. As you understand, the seismic hazard is not the same here in northeastern region of India. It is totally different. And as a result, here, no ground motion prediction equation pertinent to northeastern region of India from local seismic network has been utilized. It has been all the GMP that has been utilized is from intraslab and of course subduction zone earthquake. And and that is for reverse faulting mechanism, strike slip faulting mechanism, and also subduction zone mechanism. And what this seismic hazard map indicates that the hazard is really high from say Indo-Myanmar region, and also from near Bhutan Himalaya, and also from Arunachal Himalaya near Tezpur and all. And now if you happen to remember the what is called strain map, that particular map is really coincided with this seismic hazard map. But again, I reiterate that we don't have ground motion prediction equation out of our network. So there we have to work hard to establish the ground motion prediction equation, incorporating all the tectonic seismological domain, tectonic domain, geomorphological features, the slip rate, the focal mechanism solution, the rupture assessment, the directivity measurement. All these are an input to this particular seismic hazard assessment. So as I understand, this seismic hazard assessment map is still, there is a lot of much to be yet to be resolved, and for this particular reason. So this is the, as I said, seismic hazard map for 1 second, and this is the gross one, as you have seen already. This is for 1 second period, and this is for 3 second duration. And as I say you, for many particular cities, there are 13 populated cities. There are these 13 populated cities exactly. I mean, really, it is more than 5 million people stay in these cities. And when we see the estimated peak ground acceleration from the probabilistic seismic hazard assessment map, this is something comes around 208 centimeter per second square to 210 centimeter per second square. So at the end of the day, when we wish to build an earthquake resilient society, we have to understand that these are the prime information that we have to incorporate in our seismic design in such a complex region. So in conclusion, we know the source characterization, but here the question is, the dominant mechanism is still yet to be resolved. We know the stress map, but the directivity is yet to be resolved. Directivity is puzzling us in different seismogenic zones, and zone, which could be the probable source zone for a potential earthquake, and where really is it so, that we have to answer more rigorously. And we have done some active fault mapping. We have estimated some rupture area of 1950 in June. 1897 is still yet to be resolved. So these are some of the questions that we are still left out in this particular region of India. And above all, incorporating this particular information, what I have presented, we have estimated the seismic hazard map of India. But the question is, how much realistic it is? So this virtual workshop really a platform that I invite. Now you understand that how complex the region is, northeastern region of India is. So through this virtual seminar, I invite the international participants to collaborate with us to answer these questions, because a comprehensive study on these issues is very much required to understand the complex geodynamics of northeastern region of India to a realistic one, so that a earthquake resilient society we can build. With that note, I conclude. Thank you very much for your kind attention. Thank you so much.
Thank you very much for your excellent presentation. It reminds me the extensive fieldwork that we carried out in Arunachal Himalaya with Professor Paul Taponier of Art Observatory of Singapore. Thanks for your brilliant talk. Now, let me invite Professor J.R. Kyle, the session chairperson, for his opinion. Over to Professor J.R. Kyle.
Yes, Santanu, thank you so much. Yes, I think I have no words to really express my sincere thanks and gratitude to Saurabh. The way he touched upon every aspect of seismology, how he has effortlessly attempted to understand this, ultimately the seismic hazard map of Northeast India, and his elaboration of the two great earthquake zone, its geological implications, then coming to fault plane solutions, stress inversion. I think everything was well explained, and we are all enriched and enlightened. Thank you so much, Dr. Saurabh Baruah. I think there will be some lot of questions, so I hand over to Dr. Santanu Baruah now.
We have with us Professor Ramesh Singh from Chapman University.
Yes.
So may I request Professor Singh for his remarks.
Good evening to everybody, and for me it was too early. I'm a night owl and I work quite late. Okay, but it was a very excellent lecture, and I really congratulate Dr. Baruah for giving this. And ever since I was doing my master's, and I considered the Assam as a very complex because the stresses are from three sides, and now still it is going to be complex because you see we have drained oil and we are draining oil from Assam. And when we are draining oil, the stress regime is going to change, and also the area is subsiding. The area is subsiding, and I'm very happy that they are publishing very good papers of a 1950 earthquake, because in India, if some earthquake occur, we forget about very fast. Okay, but after seeing this, the US people, they try to hammer continuously about an earthquake to understand the processes. And this is very exciting that this institute, Northeast Institute, people are working and people are trying to do this. And I would like to see that the multi-facet parameters, the observatory, is now operational, and one has to integrate all the parameters. Okay, so once again, I thank Dr. Baruah for giving such an excellent talk, and the area is very complex, no doubt about that. And now we have so many tools available to understand the processes. Okay, so there are very interesting questions. Maybe Dr. Baruah can answer this. Okay, and I would also like to jump, answering questions. Thank you very much.
Thank you very much, sir, for your nice comments. Now, may I request Mr. Prasidjo for question and answer session. Over to Prasidjo.
Thank you, sir. With your permission, sir, I am going to read out the question answers. So the first question is, why earthquake cannot be predicted? This is a very small question of a graduate student. Please do reply.
Yeah, this question actually deserves, if we can answer, a Nobel Prize. And still till today, a lot of investment, a lot of research has been conducted, but I mean, no formidable answer could be given for these kind of questions. As you know, first great earthquake in China that has been forecasted by a lady scientist in Tangshan earthquake, and which was really came true. But again, there is another more earthquake, Haicheng earthquake, that was also predicted but could not happen. So there is always a chance that prediction is 50-50. So but the work is going on. There are several studies on different multi-parametric point of view. All the geophysical mapping is going on simultaneously and in various parts of the world. And as Professor Singh has also said, ground observations, atmospheric observations, all are being critically reviewed and integrated to answer these questions. So hopefully we'll see. But to answer this question, I would like to say that we must focus more on earthquake resilient society by developing proper seismic hazard map rather than forecasting earthquake or forecasting an imminent earthquake. Thank you for your question.
Can I add something here? Because this is from the graduate
Yes, sir.
student.
Yes, sir. You're most welcome, sir.
Yes, thank you. From the graduate student, and he or she is asking why earthquake cannot be predicted. The earthquakes are occurring 4 kilometers below the earth, and let me tell. Now the doctors after within a month or 15 days, if you are pregnant, they say that the gender of the baby. Okay, why is that? The body is so small, but here we are dealing with a large body, 4 kilometers deep, and our observation is only on the surface. Okay, so this is a very, very complex situation, and earthquake occurs in a different environment. So if we have a cross-bore hole observations inside the earth, then we might get a clue. Otherwise, and which is not possible. You see. So people are trying to observe the multi-parameters, okay, but we have to understand all kinds of signals. Thank you.
Thank you, sir, for your brilliant answer. Procedure, please go ahead.
Yes, sir. So the next question is, eastern boundary of Bhutan and Assam shows very low seismicity compared to other parts. What may be the reason, and whether this is a position of seismic gap? What is the potential magnitude for this region, and what will be the maximum focal depth for this region?
Yeah, it's a very good question. If we happen to see the seismicity map of Bhutan Himalaya, eastern part is totally devoid of earthquakes, and there is a large earthquake that occurred, in Bhutan Himalaya so far in 1872, and to the west southern boundary of Himalaya activity is prevalent, but in the northern boundary, towards northern boundary or eastern boundary, the activity is not at all. It is, we cannot say that it is, seismic gap, but yes, it's a debatable questions, and this questions has been answered that stress partitioning of Bhutan Himalaya to the Shillong Plateau is continued through the convergence, and the convergence rate is very high between Bhutan Himalaya, that is the HFT region, and the Shillong Plateau, or rather I'll say the southern part of Shillong Plateau. So that convergent rate might have caused some kind of stress partitioning in that particular region in Bhutan Himalaya. And some paleoseismological studies already been done, and that particular paleological study right at this moment say that there is no much potential right at this moment for a large earthquake in Bhutan Himalaya, and the predicted recurrence, estimated recurrence value is sometime around 700 years or so. So that's what I can say. But may I request our chairman and Professor Kayals to enlighten these questions in much more deeper depth.
No. Thank you so much, Saurabh. I think it's a very pertinent question. I think you have explained well. One more point which the other day, Professor from Canada, he was explaining, as you explained the stress partitioning, Sri Lanka is taking up most of the stress, and there is a stress partitioning, so Bhutan Himalaya is not that much stress. He also explained that Kopili fault is also by strike slip mechanism, it is also taking up much of stress of the convergence. So Kopili fault is another, you can say, another zone which is taking up much of stress, and Bhutan, that way eastern part of Bhutan is not that much stressed for generating earthquakes. One is that we explained that Shillong Plateau is taking up, then the Kopili fault is also taking up. The other explanation that Professor gave, that at the Bhutan Himalaya, that ramp, the rheological state of the rocks in that ramp zone, it is in a much more on a creeping stage than the accumulating stress. So there are 3-4 factors presumably, that stress partitioning, the Kopili fault taking up the much stress by and then the ramp, which is a stress accumulator in the Himalayan earthquake, for the Himalayan earthquakes below Bhutan Himalaya. That ramp rheologically is not taking up much stress, it is creeping, rather rheologically the rock is not strong. So I think these 3-4 factors are, as we understand as of now, are the main reasons that we don't get much earthquakes in the eastern part of the Bhutan. Thank you, Saurabh. Thank you.
Can I add here?
Yes, sir.
So, Saurabh, can I add?
Yes, sir. Go ahead, sir.
Okay.
Yes, sir. Please go ahead, sir. Yes, sir.
Thank you very much. My wild thinking about Assam, why there is a low seismicity? Because Assam is located in a triangular region. If it is only compressional, tensional forces, the two direction forces, then there is a good chance for the higher seismicity. Here, this is a triangular situation, and then it is getting balanced. And what is needed to understand this, we must enhance the dense network GPS, which can give you the direction of the stress. Okay, so that is very, very important. And also here, when I said the region is subsiding, and we should also get a vertical uplift. Okay, so this is my wild thinking, and this is a very important location. Thank you.
Thank you very much, sir. Prasad, for next question.
Yes, sir. The next question is, what is the difference between doing inversion using P wave and S wave?
Will the result the same? Yes, there are two techniques that either you can invert the amplitude of P wave as well as the S wave and the entire waveform. So there are three types of waveforms you can consider while doing a waveform inversion. And the main target is to resolve the focal mechanism solution, identify the focal mechanism solutions. So mainly, if it is a teleseismic earthquake, we basically prefer to resolve with P wave amplitude inversion. If it is very much local earthquake, we prefer to do with S wave inversion. And the most robust thing is to utilize the complete waveform while inferring the focal mechanism solutions through waveform modeling. So that's your answer.
Okay, sir. Nawazid Moli wants to know.
And for the last step, yes.
Yes, sir. Yes. Is there any possibility of reactivation of the Oldham fault in near future, which could be entirely change the topography of northern part of Meghalaya Plateau and southern part of Gwalpara and Kamrup district of Assam? Because we know that as a result of 1897 great earthquake, Sanduvir Lake was formed.
Yeah, and that's a very good question. I mean, Navajyoti, really it is a very good question. But I mean, recurrence period, as I mentioned, the 1897 rupture zone, rupture area has not been estimated as of now, as of today. We are looking forward to that. But a lot of work has been carried out, no doubt, but still that rupture area has not been resolved. Now the question is, Chandubi Lake was formed because of 1897 earthquake. But in a sense, the remnants of Chandubi and the remnants of 1897 earthquake, when we did some paleoseismological studies in Gwalpara region and near Dudhnoi region by, I mean, Professor from Institute of Science, Bangalore, C.P. Rajendran and Dr. Sukija from Enjara, Hyderabad. So in C.P. Rajendran's paper, which was published in Tectonics, where I was also one of the authors, and we found that in that particular region, the recurrence period for a large earthquake of that magnitude is something around 550 years. So as we understand that at this moment that recurrence period do not match exactly with the Oldham fault to be reactivated. So I'd request you to go to those two pioneering paper by Professor Sukija and Professor C.P. Rajendran.
Thank you, sir. So I am very much thankful to Professor Ramesh Singh, Chapman University, USA, Professor J.R. Kyle, and Dr. Saurabh Baruah for your kind support and encouragement. Now may I request Dr. Sinmoy for vote of thanks. Over to Dr. Sinmoy.
Thank you, sir. Good evening to all. Thank you for giving me this opportunity. It's my privilege to propose a vote of thanks on this session. I, on behalf of CSIR-NEIST and the entire organizing committee, would like to thank Dr. Saurabh Baruah sir for such an informative presentation. Sir, you are enlightening us. It is really helpful to understand about the complex tectonics of Northeast India. My sincere thanks goes to respected chairperson of today's session, Professor J.R. Kyle sir, for his continuous support and guidance throughout the event. I express my deep sense of gratitude to Chief guest of today's session, Professor D. Amico of University of Malta, our special guest, Professor Ramesh Singh, Chapman University, USA, and special invitee, Professor Mehdi Jareh, IIES, Iran, for being with us and encourage us. We are delighted to have you with us today. Thank you, sir. I also thank to our director, CSIR-NEIST, Dr. G.N. Sastry, for his support and cooperation. I must thank convener of this international workshop, Dr. Santanu Baruah, for giving such an amazing platform to interact with such eminent personalities in the field of seismology. Last but not least, I thank all the participants across the globe for their active participation and all the members of the organizing committee for their tremendous effort to make this international workshop a big success. With this, I thank you, all of you, once again. Thank you.
Thank you. Thank you so much.
Thank you, sir.